Hello, myself Dr. Rajesh working as a assistant professor in JSS College, Gokak. Well, in the last video, I have discussed about the hydrogen atom spectra or emission spectrum of hydrogen atom, where we came to know that hydrogen atom spectra consists of discrete spectral lines, and it consists of 5 series of spectral lines, namely Lyman series, Bohr series, Paschen series and bracket series. Here the question comes, why the discrete spectral lines are present in the hydrogen spectrum, and one more fact is that why the large number of spectral lines are present in the emission spectrum of hydrogen, even though hydrogen atom consists of only one electron. So this can be explained on the basis of Bohr atomic model. So today's lecture is therefore it is on the explanation of hydrogen atom spectra or emission spectrum of hydrogen atom on the basis of Bohr atomic model. Here, according to Bohr atomic model, the hydrogen atom or any atom consists of discrete energy levels. That means he has given the numbers starting from nucleus 1, 2, 3, 4 like that. That means if it is a hydrogen atom, it consists of energy levels like 1, 2, 3, 4. These energy levels are associated with a certain fixed amount of energy. So that means hydrogen atom consists of discrete energy levels. So in such condition, during de-excitation of electrons from different higher energy levels to lower energy levels, there is emission of a discrete amount of energy in the form of radiations of different frequency and wavelengths, which will appear as a different or discrete spectral lines in the hydrogen spectrum. Therefore, according to Bohr atomic model, the discrete lines which appear, the appearance of discrete lines in the emission spectrum of hydrogen atom is basically due to the presence of discrete energy levels in the atom. So because of the presence of discrete energy levels, when the electron jumps from higher energy to lower energy level, there is emission of a discrete amount of energy which emits in the form of radiation of a particular frequency and particular wavelength, which appears as a separate or discrete spectral line. For example, when an energy is supplied to hydrogen atom, so the electron which is present in the ground state energy level is shifted to second energy level. Now when the electron jumps from second energy level to first energy level, it will emit the radiation, or it will lose the energy in the form of radiation, which is equal to the difference between these two energy levels. So therefore the fixed amount of energy is liberated here. So that will appear in the form of spectral lines. Suppose one electron, if it jumps from third energy level to first energy level. If you take another example, in another hydrogen atom, if the electron which is present in third energy level, if it jumps to first energy level, again it will emit radiation, or it will lose energy which is equal to difference between third energy level and first energy level. So therefore the energy emitted in the form of radiation is having again a particular frequency and wavelength. Therefore these two lines will appear separately. That means a discrete spectral line will appear. Now let us see why hydrogen emission spectrum of hydrogen is showing large number of spectral lines, even though hydrogen atom contains only one electron. This is because during experiment they have taken the sample of hydrogen gas instead of taking the single hydrogen atom, which is impossible also. That is, it is not possible to take a single hydrogen atom and record its emission spectrum. So therefore they have taken the sample of hydrogen gas in the discharge tube. So that means a large number of or infinite number of hydrogen molecules were present in the discharge tube during the experiment. When the energy was supplied in the form of electric discharge, first these hydrogen molecules are converted, or they breaks into atoms. That means large number of hydrogen atoms were formed or present in the discharge tube during the experiment, and at the same time these hydrogen atoms are going to absorb a different amount of energy, and depending upon the amount of energy they absorbed, they have promoted the ground state electrons to different higher energy level. For example, in some hydrogen atoms the electrons may be promoted to first energy level to second energy level. In some other hydrogen atoms, so the electrons which is present in the first energy level, it may be promoted to second energy level. So like that, different hydrogen atoms, depending upon the amount of energy absorbed during the discharge, during the supply of energy, they have promoted their ground state electrons to different higher energy levels. Now these electrons are in the excited states. That means when the electrons are present in the excited states, we call that one as the excited states of the electrons. In the excited states of electrons, these electrons are unstable. That means they will not stay forever in the excited states only. They have a tendency to come back to the lower energy level. So therefore, during de-excitation process, that means shifting of or jumping of electrons from higher energy level to lower energy level process, these electrons which are present in different excited states jumps back to different lower energy levels with the emission of radiations of different frequencies, which appears as a different spectral lines in the hydrogen spectrum. So that means during the each transition of electron from higher energy level to lower energy level, discrete amount of energy is liberated in the form of radiation which are having a specific frequency and wavelength. Those radiations are appeared as a different spectral lines in the hydrogen spectrum. Therefore, during experiment with a sample hydrogen gas, large number of different types of downward transition takes place simultaneously with the emission of radiations of different frequency and wavelength. Hence, a large number of spectral lines are formed or produced in the emission spectrum of the hydrogen. Further, it is clear that hydrogen atom spectra consists of 5 spectral series, namely Lyman series, Bohr series, Paschen series, Brackett series and Pippin series. Bohr atomic model has also explained in what condition each series of spectral lines are produced in the emission spectrum of hydrogen atom. According to Bohr atomic model, Lyman series of spectral lines will be produced when the de-excitation of electron takes place from different higher energy levels to first energy level. That means when the electron jumps from higher energy levels to first energy level, so that will result in the formation of the Lyman series. For example, if the electron, if it is present in the second higher energy level and if it jumps to first energy level, then it will give the Lyman series spectral line. Similarly, the electron, if it is present in third energy level or fourth energy level or fifth energy level or sixth energy level, like that, any electron which is present in the higher energy level, if it jumps to first energy level, then the resulting spectral lines or series is known as the Lyman series of spectral lines. That means for Lyman series of spectral lines, the lowest energy level is first energy level. That means first energy level is the lowest energy level for the Lyman series, and the highest energy levels are lowest energy levels is Lyman first energy level, and the highest energy levels are second and third energy levels are known as highest energy level. Lowest energy levels is equal to first energy level, and highest energy or higher energy levels are 2, 3, 4, like that one. So that means Lyman series of spectral lines are produced when the de-excitation of electron takes place from different higher energy levels to first lower energy level. Therefore, the transition of electron which produces the Lyman series of spectral lines can be represented as, if it jumps from 2 to 1, third level to first level, fourth level to first level, or fifth level to first level. Here the first spectral line is produced when the electron jumps from second energy level to first energy level. This is known as a first spectral line. This is the second spectral lines. That means 3 minus 1 is the 2. That means the second spectral line will produce, Lyman series of spectral line will produce when the electron jumps from third energy level to first energy level. Similarly, the third spectral line of Lyman series will appear when the electron jumps from fourth energy level to first energy level. Thus, Lyman series of spectral lines will appear when the excitation of electrons or jumping of electron takes place from higher energy level to first energy level. So that will give the Lyman series of spectral lines. Now, Bohr series of spectral line will be produced when the electrons, that means de-excitation of electron takes place from higher energy levels to second energy level. That means if this is the hydrogen atom, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5 and 6, these are the higher energy level. Now, for Lyman series, the lowest energy level is the first energy level is known as the lowest energy level for Lyman series. For Bohr series, the lowest energy level is the second energy level. That means when the de-excitation of electron takes place from higher energy level to second energy level, that means if the electron is present in third energy level, if it jumps to second energy level, so that will produce the Bohr series of spectral line. Similarly, the electron which is present in fourth energy level, if it jumps to second energy level, it will also produce the Bohr series of spectral line. Similarly, the electrons which are present in the 5, 6 and any other higher energy levels, if they jump to second energy level, then definitely there will be formation of Bohr series of spectral lines in the emission spectra of hydrogen atom. Therefore, for Bohr series of spectral lines series, lowest energy level is second energy level. That means the second energy level is known as lowest energy level for the Bohr series, and highest energy levels are third, fourth, fifth, so like that. Therefore, the electronic transition which produces the Bohr series of spectral lines can be represented as 3 to 2, 4 to 2, 5 to 2, like this one. If the electron, if it is present in third energy level, if it jumps to second energy level, so it will produce the first Bohr series of spectral line. That means first spectral line of Bohr series is produced when the electron jumps from third energy level to second energy level, and the second spectral line of Bohr series will be produced when the electron jumps from fourth energy level to second energy level. So like that, whenever the de-excitation of electron takes place from different higher energy levels to second energy level, that will result in the formation of Bohr series of spectral lines according to Bohr atomic model. Similarly, Paschen series of spectral lines will be produced in the emission spectrum of hydrogen when the de-excitation of electron takes place from different higher energy levels to third energy level. That means if it is a hydrogen atom, and it is energy level 1, 2, 3, 4, 5 and 6. Here for Lyman series, the lowest energy level is energy level 1 is the lowest energy level for the Lyman series. Second energy level is the lowest energy level for the Bohr series. Now for Paschen series, third energy level becomes the lowest energy level. So that means when the de-excitation of electron takes place from different higher energy levels to third energy level, so that will produce the Paschen series of spectral lines. That means when the electron is present in the fourth energy level, if it jumps to third energy level, so that will produce the first spectral line of the Paschen series. So that means the electron which is present in the fourth energy level, if it jumps to the third energy level, so it will produce the first spectral line of the Paschen series. Similarly, if the electron present in the fifth energy level jumps to third energy level, so that will produce the second spectral line of the Paschen series. Thus, Paschen series of spectral lines will be appeared in the emission spectrum of hydrogen atom only when de-excitation of electrons from different higher energy levels takes place to the third energy level. That means when the electron which are present in the fourth, fifth, sixth, seventh, eighth and like that, if they jump to third energy level, then definitely that will result in the formation of, or they will appear as a Paschen series of spectral lines in the emission spectrum of hydrogen. Therefore, for Paschen series of spectral lines, lowest energy level is the third energy level. That means third energy level is the lowest energy level, and the higher energy levels are fourth, fifth, sixth and like that one. Therefore, the transition of electron which produces the Paschen series of spectral lines can be represented as when the electron jumps from 4 to 3, 5 to 3, 6 to 3, etc. like that. Similarly, according to Bohr atomic model, the bracket series of spectral lines will appear when the de-excitation of electron takes place from different higher energy levels to fourth energy level. So that means if this is the hydrogen atom, energy level 1, 2, 3, so like this one. So therefore, for bracket series of spectral lines, the lowest energy level will be the fourth energy level. So now, if the electron, if it is present in fifth energy level, if it jumps to fourth energy level, definitely it will produce the first spectral line of the bracket series. Similarly, if the electron, if it is present in 6th energy level and if it jumps to 5th energy level, definitely it will produce the second spectral line of the bracket series. Similarly, the de-excitation of electrons from different higher energy levels to 4th energy level definitely will result in the formation of the bracket series of spectral lines in the emission spectra of hydrogen atom. Therefore, the transition of electron which will produce the bracket series of spectral lines can be represented as, now the fourth one is the lowest energy level, so that means higher energy level it will start from 5th, that means 5th to 4th energy level jump of electron. That means if the electron is present in the 5th energy level, if it jumps to 4th energy level, so this will produce the first spectral line of the bracket series. Similarly, 6th to 4th and 7th to 4th will give the bracket series of spectral lines. Similarly, the last series of a spectral line, that means a p-point series of spectral lines will be produced in the emission spectrum of hydrogen atom when the de-excitation of electron takes place from different higher energy levels to 5th energy level. So that means for p-point series of spectral lines, 5th energy level will become the lowest energy level. If it is the hydrogen atom, energy level 1, 2, 3, 4, 5, 6, 7, 8 like that. So that means first energy level is the Lyman series, lowest energy level. Second lowest energy it represents the Bohr series. Third energy level it becomes the lowest energy level for the Paschen series, and fourth energy level becomes the lowest energy level for the bracket series, and similarly the fifth energy level will become the lowest energy level for the p-fund series. Now if the electron present in the 6th energy level, if it jumps to 5th energy level, definitely it will produce the first line of the p-fund series. And another electron, if it is present in 7th orbital, and if it jumps to 5th energy level, again it will produce the p-fund series spectral line. Like this one, de-excitation of electrons from different higher energy levels to 5th energy level definitely will result in the formation of the, or it will produce the p-fund series of spectral lines in the emission spectrum of hydrogen atom. Now therefore the electrons, the electronic transition or jump of the electron which will produce the p-fund series of spectral lines can be represented as, that means 6 to 5, 7 to 5, 8 to 5, so like that. That means a electron, if it is present in 6th energy level, higher energy level, 6th orbital, 6th orbit, if it jumps to 5th energy level, that means that will produce the first p-fund spectral line. Similarly, if an electron present in the 7th energy level, if it jumps to 5th energy level, again it will produce the p-fund series of spectral lines. This is how Bohr atomic model has explained in what condition Lyman series, Bohr series, Paschen series and bracket series and p-fund series of spectral lines will appear in the emission spectra of hydrogen atom. Further, Bohr has also calculated the frequency of each spectral line in each series of spectral series by using Rydberg formula, Rydberg equation, just by substituting the n1 and n2 values. Here nu bar, that is a frequency in terms of wave number, is equal to the r, that is a Rydberg constant, into 1 by n1 square minus 1 by n2 square in terms of per meter. That means here n1 is the lowest energy level and n2 is the highest energy level, higher energy level. So in order to calculate the spectral frequency of spectral lines in each series, one has to put the value of n1 and n2 as shown in this diagram, or as shown in this table. That means in order to find out the spectral line frequency of spectral lines in a Lyman series, we have to put n1 is equal to 1 and n2 is equal to 2, 3, 4 like this one for Lyman series. So that means if you want to calculate the frequency of a first spectral line of Lyman series, so in order to find out the first spectral line of the Lyman series, we have to put the n1 is equal to, that means the lowest energy level, that is 1, n1 is equal to 1, and highest energy level, that means higher energy level is equal to n2 is equal to 2. Now by substituting these values, one can easily get the frequency of each spectral line in the each series. So that means for Bohr series or in a Lyman series only, if you want to calculate the frequency of second spectral line, then put the value of n1 is equal to 1 and n2 is equal to 3. That means when the electron jumps from third energy level to first energy level, definitely it will produce the second spectral line. Therefore, in order to find out the frequency of second spectral line of the Lyman series, we have to put the value of n1 is equal to 1 and n2 is equal to 3. Similarly, one can easily calculate, or Bohr has also calculated the frequency of each spectral line, in each series by substituting the n1 and n2 values as follows. That means for Bohr series, if you want to calculate the frequency of first spectral line, so then we have to put the n1 value is equal to 2 and n2 is equal to 3. Similarly, if you want to calculate the frequency of second spectral line of Bohr series, we have to put the value of n1 is equal to 2 and n2 is equal to 4. Similarly, for Paschen series, we have to put the value of n1 is equal to 3 and n2 is equal to 4, 5, 6, like that one. Similarly, for bracket series, n1 value will becomes 4 and n2 value it will vary from 5, 6, 7, 8, like that one. Similarly, the last series, if you want to calculate the frequency of each spectral line in P-Fund series, we have to put the value of n1 is equal to 5 and n2 is equal to 6 or 7 or 8. That means if you want to calculate the frequency of first spectral line of a P-Fund series, we have to put the value of n1 is equal to 1 and n2 is equal to 6 in the Rydberg equation. So thus, Bohr has also calculated the frequency of these spectral lines, that means the first three series of spectral lines. He has calculated the frequency of all the spectral lines, that means 1 to 6 spectral lines in the Lyman series, Bohr series and Paschen series, and he compared with the experimentally observed value of frequencies. Here there is a great agreement between the theoretical value as well as the experimental values, which has supported or which becomes the strongest support for the Bohr's atomic model. Thus, Bohr has compared the calculated frequency of each spectral line. That means first 6 spectral lines frequency he has calculated with the help of Rydberg equation, and he compared the values with the experimentally what he got. So that means here first frequency of first spectral line, it is 82.25. It is the experimentally observed value, whereas the calculated value is also same, 82.2. Similarly, the second spectral line frequency is 97.5 with according to experimental value, and calculated value is also same. Similarly, the third spectral line is showing 102.8 experimentally observed value, whereas the calculated value is again 102.7. Similarly, the fourth spectral line frequency is 105.2 and it is experimentally observed, whereas the calculated value is 105.2 only. Similarly, the frequency of a fifth spectral line of Lyman series is 106.3 experimentally observed, whereas the calculated value is also 106.2 value. Therefore, the last spectral line frequency is 107.2, whereas if it is an experimental value, whereas the calculated value is also 107.1. That means 107.2 is the experimentally observed value, 107.1 is the calculated value. Thus, he has calculated the frequency of each spectral line in case of Bohr series and Paschen series also, where experimental values as well as the calculated values are in great agreement with each other. That means this has supported very strongly about the Bohr atomic theory. So this is how Bohr atomic theory has explained successfully atomic structure, that means arrangement of fundamental particles in an atom. And he has also shown, the Bohr atomic model has also given an expression to calculate the radius of nth orbit as well as calculation of energy associated with an electron present in the nth orbit also, and it has also shown the how to calculate the frequency of emitted radiation when the electron jumps from higher energy level to lower energy level. Further, Bohr theory has also explained why the hydrogen emission spectrum consists of discrete spectral lines. It has also explained this one. Further, it has also explained why there is a large number of spectral lines even in the emission spectrum of hydrogen atom, even though the hydrogen atom contains only one electron. But he has also calculated the frequency of each spectral lines, or And further, this theory has also explained in what condition these spectral lines are these spectral lines are going to produce in the hydrogen spectrum. For example, in what condition Lyman series will appear, in what condition Bohr series will appear, in what condition bracket and Paschen series will appear. So far the Bohr atomic model has explained almost all facts about the atomic structure and emission spectrum of the hydrogen atom. So in spite of such a successful explanation about the facts with respect to atomic structure, Bohr theory has certain drawbacks which are known as limitations of Bohr atomic theory, which we will discuss in the next video.